Welcome back again. Now we will continue with session 2 with 4 more projects. And we will continue in India too. And the next project, that is from Larsson and Torbror Limited. Smart CBG-fied galvanizing system for sustainable manufacturing and emission reduction. So please start your presentation.
In a world racing against climate change, L&T made a promise: water neutral by 2035, carbon neutral by 2040. A promise not written in reports, but etched into responsibility. But promises demand action, especially where the fire burns hottest. At TLT Works Pithampur, every transmission tower follows a precise manufacturing journey, from design to fabrication, to galvanizing and dispatch. But among all these stages, one process contributed the most to our carbon footprint. Our galvanizing furnace consumed 836 tons of LPG every year, releasing 2,492 tons of CO2 into the atmosphere. This created 3 critical challenges: environmental impact, resource depletion, and the absence of real-time energy monitoring. To advance toward carbon neutrality, this had to change. The galvanizing process begins with surface preparation. Steel passes through degreasing, pickling, rinsing, and fluxing, removing oil, rust, and impurities to ensure strong adhesion. Next, the clean steel is immersed in molten zinc at 450 degrees Celsius. A metallurgical bond forms, creating a corrosion-resistant layer. Even if scratched, zinc protects steel through sacrificial corrosion, extending its service life for decades. We evaluated alternative fuels. LPG emits 2.98 kilograms of CO2 per kilogram of fuel. LDO emits 3.1 kilograms. But compressed biogas emits only 0.005 kilograms, making it almost carbon neutral. And with a calorific value equal to LPG, CBG became our preferred alternative. With detailed analysis and quality-driven brainstorming, we decided to transition our galvanizing furnace from LPG to CBG. We visited Indoor's Gobardhan plant, Asia's largest biogas facility. We verified pressure, purity, and moisture content, and secured a reliable supply of compressed biogas for continuous furnace operations. Our first trial failed. The second failed. Moisture choked the burners. Pressure dropped. The flame collapsed. But through every setback, quality guided our next step. To solve contradictions, we applied TRIZ, using Principle 35 to redesign a 12mm tapered nozzle, achieving 98% flame stability and a 10% increase in thermal efficiency. Using design of experiments, we optimized air-fuel ratios and pressure levels, reducing CO emissions to below 68 parts per million. Through Six Sigma, we controlled CO2 intensity to 0.005 kilograms per kilogram of fuel, within a tolerance of plus or minus 0.5%. And with 12 PDCA cycles, we achieved flame length consistency within plus or minus 2% at 150 millibar. AGSM Gateway enabled real-time mobile monitoring, bringing digital precision to our combustion system. We identified key risks: pressure surges, moisture carryover, and ignition failure, and mitigated them using safety interlocks, heated gas trains, pressure relief devices, and automated shutdown logic. Our solution was a multi-stage pressure regulation system with heating, moisture removal, dual ignition, and IoT-based control. This innovation is now protected under PCT/IN 2025/050160 and Indian Patent Application 2024-411-01107, recognized for novelty and inventive step. With this breakthrough, TLT Pithampur became India's first galvanizing facility to operate entirely on compressed biogas. One morning, the flames stood steady, quiet, clean, and perfect. A flame reborn for the planet.
Our results are measurable and impactful. CO2 emission intensity reduced from 3.01 to 2.75 kilograms per kilogram of fuel. Specific consumption reduced from 11.6 to 10.5 kilograms per metric ton. Combustion efficiency increased from 89.2% to 97.8%. And system uptime improved from 92% to 98%. Our annual CO2 reduction now stands at 3,800 tons, equivalent to planting 171,818 trees every year. This initiative advances SDG 7, Affordable and Clean Energy, SDG 9, Industry, Innovation and Infrastructure, SDG 12, Responsible Consumption and Production, SDG 13, Climate Action. Circular economy benefits include 550 tons of municipal waste converted into 17 tons of CBG and 100 tons of organic compost. Digital twin integration now tracks 470 data points per hour, enabling predictive decarbonization. And this model is being scaled across L&T facilities, achieving up to 42% OPEX reduction.
Neil Armstrong said, "One small step for man, one giant leap for mankind." This is our small flame, our giant leap toward a cleaner world.
Yeah, thank you very much for the presentation. For a change, I will start with a few questions. Actually, two simple questions. The first one is about the leverage potential. In what way can this be expanded to other areas? And of course, this is dependent on availability of CBG gas.
Yes, sir. It can be implemented horizontally, can be deployed in other areas also. But as you said, the availability remains a constraint. If the gas is available, I think there should be more and more usage in such areas, like in our case for galvanization, like some more productions. Other factories in India, only we are around setting up 30 plants with the help of our Prime Minister, Mr. Narendra Modi. So these type of plants will be located in various areas of the country. So I think the supply would not be a constraint in near future, sir. So in that case, it can be horizontally deployed also. So that's why we have filed a patent for this process. So others can also take the advantage and can change their processes also.
Okay, thank you. I have a second question. In the text, there's mentioning of a safety risk in using LPG. Is that not present when you use CBG?
Yeah, in the case of LPG, sir, the shade was located just beyond the plant. It was like within the plant only, all the setup for LPG. And the CBG station is situated around 250 meters away from our firing unit. So there's a lot of distance. So we can say the hazard we have eliminated totally in this.
Okay, good. But of course, I just want to see. Basically, you could have put the LPG installation also 250 meters away. Am I
But
correct?
that would not solve the sustainability.
That's true. That's true. I'm
measure.
just looking at that. And actually, the same thing, because you introduced a very state-of-the-art control system with Internet of Things control system. Again, but correct me if I'm wrong, that is independent of the gas you use.
Yeah. So we
Okay.
have employed this system to monitor the usage, to track the temperatures, humidity, and all. And it can be like implemented on LPG also. But what we are doing here is to like reduce our carbon footprint from the atmosphere. So we are like more focusing on resource depletions also, like monitoring, measuring. So like from manual monitoring, we have shifted to that IoTs and HMIs and all.
Okay, thank you. That were the questions I had. We still have time for some additional questions. Ravikant?
I have one question, which is on the quantum of carbon dioxide emission, which is reduced. So if I saw your presentation correctly, if you could put up one of your last slides, it said going down from 3.01 to 2.75. Is that correct?
In case of CBG, sir, it is near about zero. If we consider it in circular economy, like it is a carbogenic cycle. Like the gas is emitting carbon dioxide, but it is getting neutral because it is being generated by the waste created by the city. So the biodegradable waste is converted to gas. Then again, the plants are consuming that CO2. So in that case, the net effective carbon dioxide emission comes to 0.005 kgs per kg of CBG gas. So it is emitting
currently what proportion of your total requirement is on CBG and how much is still on the old fuel?
Around 72% we have like we have switched to CBG for in our 100% of contribution. We have 72% we have achieved, sir.
Okay. Thank you.
Okay, thank you. Any other questions? Okay, if not, I want to thank you again. Okay, Samaya, sorry.
Yeah. Sorry. So thanks for your presentation. My question is about the scope of your emission calculation. Because you mentioned zero emission, did you consider a scope 3 emission as well, or you're just talking about the scope 1 and 2 emission? Your measurement is across. Sorry, go ahead, please.
Can you repeat the question, ma'am?
Yeah, so my question is the emission that you reported. Could you please clarify if that's across scope 1 and 2, or it also includes the scope 3? Because when you mentioned zero emission, it might not just include the scope 3 emission calculations in your report. So I want clarification on this.
So I think it is under all the scopes, ma'am, scope 1, 2, 3, because the gas is being produced by the waste that is being created by the city. So no net carbon emission is coming from there, and also is zero. Like we are emitting some CO2, but that CO2 is being neutralized by the carbogenic cycle, because it is being generated by the waste that has been created by the city. So it is a biodegradable waste. So no electricity and other energies are being used to convert it into gas. So from its generation itself to the consumption, it is totally carbon neutral, ma'am. So scope 1, 2, 3 all falls.
Sorry to interrupt. When you mentioned scope 3, it includes transportation and everything. So that could not be zero. That's why
transportation also, the vehicles which are carrying this gas are also running on CBG. So there is totally net.
So across all the supply chain from where
supply chain is also managed by this CBG only. The vehicle which is carrying this gas in cascades is also run by CBG gas only.
Okay, thank you.
Okay, thank you very much. And nicely on time to move over to the next project.
Yes, thank you, Willy.
Thank you.
And now the next project is, we are continuing in India here, so it's GSV Steel Limited. And the project is about CTP improvement through seed. So please start your presentation.
This is Veer Brahmacharlu presenting on behalf of a team consisting of Mr. Ganesh Shetty, Sudhakar, Ankit Das, Nasim Obaid, and Ms. Sinchana. This is the process flow of JSW Steel, Vijayanagar Works. The raw materials, that is iron ore, flux, and coal, are processed to produce sinter, pellet, and coke. Sinter, pellets, and coke are charged in blast furnace to produce hot metal, and pellets are charged in DRI shaft to produce DRI. The steel scrap, hot metal are charged in basic oxygen furnace to produce liquid steel. The steel scrap and DRI are charged in electric arc furnace to produce liquid steel. The liquid steel is cast in continuous casting machines to produce slabs and billets. The slabs are rolled in hot strip mill and cold rolling mills to produce flat products. The billets are rolled in wire rod mill and bar rod mills to produce long products. The byproduct gas generated from coke oven, corex, blast furnace, LD, and DRI are mixed is called mixed gas. The mixed gas is used for various heating applications in the entire integrated steel plant. This is the roadmap for decarbonization consisting of renewable energy, green hydrogen-based steel making, carbon capture, utilization, and storage. Here is the strategic plan to reduce the current CO2 footprint from 2.5 tons to 0.8 ton per ton of crude steel. Our incremental decarbonization initiative, SEED, stands for Sustainable Energy, Environment and Decarbonization. This is a dashboard to monitor CO2 footprint. There have been several quality improvement programs through SEED. Our case study, injecting coke oven gas into the sinter bed, showcases improvement in CTP, critical to process. We also improved the production and CTQ, critical to quality. These are the technology, energy efficiency, environment, quality, and sustainability milestones. The idea is to substitute the fossil fuel partially by coke oven gas. This is the overview of the sinter plant showing the location of the COG injection system. Here is a brief introduction to the sintering process. The pilot trials began in 2019 using sinter pot facility. It did not have arrangements to inject gases, so we introduced gas injection system and conducted trials. The product sinter was dense, had higher strength, and better elevated temperature properties. Due to parametric interplay which is inherent to sintering process, the alpha in the design of experiment showed 1.4. Oxygen, which can improve the combustion efficiency of coke, and liquefied petroleum gas LPG as an alternate gaseous fuel were injected to see their effects. The coke oven gas has about 57% hydrogen, a carbon neutral source of heat and reductant of the iron ore. When injected, COG outperformed LPG. Hydrogen in the COG enhanced FeO formation. Superior mineralogical phase assemblages were noticed, which resulted in enhanced properties of the sinter. The voice of the process indicated improved thermal regime and mineralogy. After proving the concept, we scaled up by designing COG header, nozzles, and installed in Sinter Plant 4 in 2020 during COVID times. This is the scheme of the injection system. The design involved 3 headers of 150 cubic meter per hour capacity, each and nozzles to inject COG close to the sinter bed. Multiple trials were conducted to fine-tune the process, and we continued injecting for more than 1.5 years. Sinter plant 2 and 4 consume the base mix from a single source. With COG being injected, sinter plant 4 consumed less coke, as seen by the coke run chart. The tumbler index and suction increased due to COG. Analysis of variance shows the process capability of FEO increased from 0.27 to 0.35. After successfully proving the industrial scale concept, the COG injection system was installed in sinter plant 3, which is double the capacity of sinter plant 4. Data analysis of sinter plant 3 indicated higher tumbler index and process capability. In both sinter plant 3 and 4, the elevated temperature property RDI remain unchanged. Hypothesis testing confirmed that the sintering process is not delayed due to prolonged thermal regime. Exponentially weighted moving average confirmed an increase in production of 800 tons per day, that is about 6%. With this improvement, it is possible to save about 30 Indian rupees per ton of sinter or 2.3 million Indian rupees per annum directly. Thank you.
Yes, thank you very much for the presentation and the project. Any questions from the team? See what I have here. One of the Ravikant, you have a question?
Go ahead.
Go ahead. No,
Yeah, go ahead.
I'll ask mine first.
Please.
One of the elements of the award talks about leverage potential, and this is a very good and interesting project. But it's obviously very much focused on, in this case, sintering and within the steel plant. Do you see any other areas where there could be an application for this technology, this idea of injecting gas into a stream of material?
Beyond integrated steel plant, sir?
Yes. If you could think about, I don't know. I know all about steel plants and sintering in steel plants, but I was wondering if the concept as such, if you see any other application areas.
Well, in integrated steel plant, there are plenty of applications, including blast furnace, reheating furnaces, DRI. But beyond integrated steel plant, I think we can export the gas, make a syngas out of it, or get hydrogen out of it and use for district heating or other heating applications.
Okay, good. Thank you. Ravikant.
Yeah, thanks, Willie. Thank you, guys. I have one question. You showed two capability indices at two different places, and both of them showed, I don't know which characteristic you mentioned, but they seem to be pretty low at 0.27 and 0.34. So two questions: which quality characteristic were you measuring? And two, why is your process capability still very low?
Yes. So in the existing process, the capability is about 0.2, 0.25 only, because FEO is transforming from Fe to O3 when you provide a source of heat, that is carbon. But there is a limit on which the FEO should be there in the product, which is 9 to 10.5. The reason why the capability is not more than 1, for example, you wanted to have the best fit or 1.3, something like that, then it is not possible because there is a limitation on the upper limits. The customer wants 9 to 10.5.
Now, what is the characteristic that you're measuring?
FeO.
Presence of FeO content.
Ferric oxide. Yes, yes.
Ferric oxide content. Okay.
Yes.
So your specification is 9 to 10, but you can get only a very low number.
10 points. Yes, yes.
Okay. Is this a limitation of technology or is it a limitation of your process?
Limitation of the process.
Okay. So in a sense, what I hear you saying is that the implementation of this particular COG injection did not change the ferric oxide content. Is that correct? It didn't materially change the amount of
supposed to be changed. No, with the usage of alternate fuel, the FeO must remain in the specification limits.
Okay.
It should not overshoot or it should not go below the lower control limit.
All right. Thank you.
It must be maintained, and we adjust the process accordingly so that it remains within the specification limits.
Sorry, one more question on the. So this is a multi-year project where you started in 2019 and you did pilots and so on. And so what was the total capex and opex impact, and what is the payback of this project?
I think Mr. Ganesh should give the financial figures. Ganesh, have you joined?
No, sir, not at joint, sir.
Can you share the capex figures? In SP3, how much was the spend? And
Yes.
Sir, I think it's about 15.
Yes.
May I add some points, sir, actually? At our integrated steel plant, this coke oven gas is abundantly available, sir. Actually, instead of flaring, we are injecting into our process. There we are getting the CO, means coke reduction, 3 to 4 kg of coke reductions. For the sintering process, we need to add this coke solid fuel. We are alternatively, we are using this gas injection and we are getting a savings of coal or coke addition by 3 to 4 kgs.
So no hardware changes were required.
I will share you the with respect to cost also, sir.
No hardware changes were required.
No, there's a lot of piping, good preparation.
Okay, thank you.
Carlos, you still have a question?
Yes. May I go ahead?
Yeah, go ahead. We have a very bad connection with Vera, so
no, there has to be pipeline.
Can't hear anything actually.
Go ahead, Jose Carlos. We'll see if
yes,
we can get the answer.
I'll try. I wanted to go back to the CPK and congratulations on your very nice project. The specification limits from 9 to 10 to 0.5. You indicate that you already went from 0.27 to 0.35, and you have indicated in the previous question that there are limits. But however, what do you envision? What would be the objective? Can you go back? Can you go up from 0.35 to 0.5 or maybe 1? What would be your approach on that?
Sir, once again, can you repeat, sir?
My question is, how, in your objectives for the CPK, for the capability index, for the FeO, how high can you envision you can get for that, improving your capability index, which is actually very shifted to the upper specification limit?
Sir, in general, normally for the sinter plant, for the blast furnace requirement will be the 9 to 10.5 only. If it is whenever it is increasing beyond 10.5, that will not be suitable for the blast furnace operation. There they need to add the more coke reactions. So more solid fuel direct coke consumption will be increased at blast furnace. So they will restrict maximum 10.5 only.
Okay, let me answer this question if I'm audible. The process capability maximum possible is for this process 0.6, 0.63 to be precise. I hope the answer is the question is answered.
Right. Yeah. And would it make sense to try to center the distribution?
Yes. See, this was experimental data. Some data was plant running data. So there you could see the dog bone structure. These disturbances were coming from the base mix. The carbon is certain percentage of carbon is already added to the base mix, and a small percentage of carbon is added in the sinter plant. If the base mix has got huge variations, then I am injecting additional fuel, which is coke oven gas. As a result, what happens is there may be a very high amount of FeO than expected, or if the coke is too less, the FeO that is produced will be less than the standard. Therefore, you were seeing at the dog bone distribution. So there were a lot of complexities involved in this process. Now it is almost matured. We can say that yes, we can install in a new sinter plant. Yeah, it's an ongoing development.
Sure.
Okay. Thank you very much. Again, in the sake of time, we'll have to stop the discussion here. Thanks again. And we can move on to the next.
Yes, thank you, Willy. Now it's time for the next presentation that is coming from Cummins India Limited. The project is about GHG emission reduction through optimized engine test cycles and energy management. Please start your presentation.
Good morning, respected jury members. First of all, let me thank you that we got an opportunity to present our case in terms of quality, role in sustainability towards the Destination Zero goals. It is of immense pleasure to present our case from Cummins India Limited on the engine test cycle optimization that we have worked through in terms of our quality team's efforts towards meeting as well as the sustainability goals. This is the flow of the presentation where we will give you an overview in terms of what is the project background all about, and then what are the steps that we have taken, what are the tools and the approaches that has been done, and then finally what the results have really come out of the project. As a part of our brand promise in terms of powering our customers through innovation and dependability, we are always committed to innovating for our customers to power their success. This is in alignment with our vision, along with our Destination Zero goals, which happens to be our corporate strategy. With that in mind, I'll just give you an overview in terms of the Destination Zero goals that we are talking about. And if you really see the first goal, which talks about the facilities energy in terms of the greenhouse gas emissions reduction by 50% from the base level of 2018, at the year of 2030, we are looking for reducing the overall GHG emissions by 50%. With that in mind, the team started looking out in the opportunities, how quality function can really work towards in terms of contributing towards this Destination Zero goals. Definitely one of the areas that the team identified is where we test our engines post-production in our test cells. This consumes a lot of diesel because of the test cycles that are used to check the product in terms of the performance for the customers and for the customer specific requirements. The team really thought through in terms of how can we bring forward the overall GHG emissions by optimizing the test cycles. Is there an opportunity out over there, and can we really look forward to in terms of improving the quality without impacting or improving the GHG emissions reductions? So the team, a Six Sigma team was formed. Now, Cummins has a very good culture of Six Sigma, and it is embedded in the culture of the organization. We have dedicated roles of master black belts, and there are people who also do projects as a part of the green belt. So a Six Sigma team was formed with the black belt taking a lead in terms of what can be done in terms of the test cycle optimization, because that was the major area that can be an opportunity when it comes down to the GHG emissions reduction. So base work was done in terms of checking what was the level of test cycles that were being used for the current products and the platforms out over there, and what are the opportunities also out over there in terms of the operations, that is of the auxiliary units that support the test cell entire system. All put together, can we have an opportunity to bring down the scope 1 and scope 2 GHG emissions without impacting the quality. And definitely energy management system was one of the key enablers that helped us in terms of really measuring, monitoring and identifying the gaps in terms of what can be done differently in terms of the scope 2 generation and consumption of electricity as well. So with that project background, the team started really collecting data in terms of each of the platforms, what was the original test cycles and what can be the next level through the CAE analysis to check for in terms of whether the revised test cycles that the team was trying to contemplate to the simulation tests, when actually applied in the test cells during the testing cycles, would yield the same result or not, and would it be having no long-term impact when the engine is already in the field. With that premise in mind, the team started doing a lot of data mining in terms of collecting the data, in terms of the test cycles parameters, and in terms of collecting and trying to really project through the simulation analysis. A lot of tools were used like ANOVA and multivariate analysis. And overall results, although I'll come to it in the last slide, but overall results that started coming out that for all the 8 platforms that the team chose, the average time of testing came from 30 hours to 19 hours, which was a substantial reduction.
Start.
Greetings, Judy. I'm Ashutosh Jha. I am from Tata Motors Commercial Vehicle Engineering side from Pune, India. I will let you through our presentation. Our innovation idea is driving sustainability through low carbon footprint material innovation for Tata vehicles. This is the content for our presentation. We will explain you this content one by one. This is executive summary. So we know the climate change is one of the most pressing challenge for our time, with global and national target pushing for significant CO2 reductions. Tata Motors commercial vehicle has committed to achieve net zero emission for our commercial vehicles by 2045. We adopted a quality-driven framework using advanced tools to ensure our solutions were both robust and sustainable. Innovations in material and process optimization played a key role in reducing our environment print. If you will see the impact, these innovations led to a CO2 reduction of nearly 969 tons annually, which is equivalent to planting over 15,000 trees. We also achieved significant saving in paint, fuel and material costs while improving air quality by reducing the volatile organic compounds. Our efforts directly contributed to 4 key sustainable development goals, including climate actions and good health. This alignment ensures our innovations are not only impactful but also globally relevant. Through innovation, quality and commitments, Tata Motors is driving meaningful change towards a sustainable future for commercial vehicles. This is introductory slide. So basically, if you will see this slide on vertical axis, we have mentioned the offerings, whether that is sustainable or not. On the horizontal slide, we are saying the how efficiently we use the resource. If you will see, we need to move from the bottom left corner to the top right corner. which is the sustainable development, the true sustainable development, where we will use the resource efficiently and the offerings will be sustainable. Let's now look at the core challenge we are addressing, which is reducing CO2 emission in truck manufacturing. See, the automotive sector, particularly commercial vehicle, is a significant contributor to carbon emission and resource depletion. Within this, one of the most energy intensive and heavy area is the paint shop operation. These operations rely heavily on baking oven and consume large volume of materials, and this leads to three major issues: a high carbon footprint, which directly impact our sustainability goals; the second, elevated operation cost driven by energy and material inefficiency; and third, the growing risk of non-compliances with global climate targets like the Paris Agreement and India's national commitment. With Tata Motors commercial vehicle aiming for net zero by 2045, we recognize that incremental challenge won't be enough. What's needed is a transformational shift. That's where innovative low carbon solutions that reimagine how we operate. Now, this challenge set the stage for the approach and innovations we will discuss next. To understand where we can make the biggest impact, let's take a closer look at the energy consumption across the paint shop process. This flowchart represents the typical stages involved in painting a truck body, starting from body in white and ending painted BIW. Now the process begins with pre-treatment followed by e-coating, both of which consume significant energy and material resources. As we can see, multiple baking stages and material applications contribute heavily to overall energy consumption and carbon footprint. This analysis is critical as it helps us identify which step offer the greatest opportunity for optimization and innovation. Reducing energy consumption in these stages is not just about cost saving, it's about aligning with our net zero goals and driving sustainable manufacturing practices. To further understand the challenge, let's look at the energy consumption across different stages of vehicle manufacturing. This analysis, based on industry data and internal assessment, break down energy uses into key areas, which are body shop, paint shop, line, motor pool, and shipments. But the most striking insight comes from the paint shop. The paint system alone consumes between 30% to 50% of the total energy and material used in entire manufacturing process. This makes it the single largest contributor to energy consumption and carbon footprint in our operation. Given this, it's clear that any meaningful reduction in CO2 emission must begin with rethinking how we operate our paint shops. And this insight has guided our innovative efforts and our focus on the paint shop energy consumption and material consumption reduction, which we will explore in the next section. To drive meaningful change in sustainability, we did not rely on guesswork. We followed a structured, quality-driven methodology. At the heart of our approach is sustainable material innovation. This is the central theme that guided every decision and improvement we made. Surrounding this are the 7 key quality tools and methodology that enabled us to deliver robust, scalable, and impactful solutions. Together, these tools form a comprehensive framework that not only improved our process but also aligned them with our sustainability goals. This methodology was key to achieving the results we will now explore in the impact section. These slides explain the methodology and quality tool, what we have used and how that has helped to achieve sustainability and reduce CO2 emission in our project. So first is quality functional deployment, QFD. This has helped us convert customer and sustainability need into material design targets such as corrosion protection combined with a low carbon footprint. Design of experiment, DOE tools allows us to to utilize and optimize sealant and E-coat formulation, reducing material energy uses with minimal trials. When we applied the DFMEA, design failure mode and effect analysis, to identify risk to integrating new material and processes, ensuring durability and safety while reducing energy intensive steps. Through RCA root cause analysis, we pinpointed high energy steps like the pre-gel oven and to eliminate them for significant energy saving. Using Kaizen, we achieved continuous improvement during lab, pilot and plant trial, driving key sustainability gains. Our life cycle assessment LCA quantified CO2 emission reduction and validated environmental benefits across the product life cycle. Finally, total quality management embedded sustainability into our organizational culture and ensured a strong cross-functional alignment. Together, these tools formed a robust framework that enabled us to deliver impactful sustainable innovation. This slide shows the timeline. So from the starting till the end, this slide also shows where at each milestone what quality tools has been used and how they have helped achieve this final goal. This slide showcases the key innovations that help us significantly reduce energy and material consumption in our paint shop operations. Let's start with the process flow. Traditionally, the paint shop involves multiple stages starting from BIW, moving through pre-treatment, e-coating and several baking steps before reaching the final painted BIW. Now, two major innovations were introduced in this flow. First is the E-coat stage. We developed advanced high-throw power E-coat. This was achieved by incorporating a branch epoxy resin structure with flexible hydrophobic segments, and this result reduced both material consumption and baking temperature, leading to lower energy uses. The second, we introduced a WOW sealant, which is wet on wet sealant. This breakthrough allows us to eliminate baking stage 2 entirely, which was previously a major energy consumer. By making this oven, we achieved a substantial energy saving and reduced operational complexity. These innovations were not just about efficiency, they were designed with a broader sustainability focus. As highlighted below the diagram, our goal included reducing material consumption, reducing energy consumption, eliminating hazardous steps, minimizing waste and utilizing waste effectively. In summary, by developing a high-throw E-coat and WOW sealant, we have made significant strides in reducing both energy and material consumption, aligning our operation with our net zero goals and global sustainability standards. This slide summarizes the tangible outcome of our sustainability initiatives and how they align with the United Nations Sustainability Development Goals. The 4 United Nations Sustainability Development Goals, SDG 3, which is good health and well-being, SDG 9, which is industry innovation and future, SDG 12, which is responsible consumption and production, and SDG 13, the climate actions, are directly impacted as prescribed in the table above. These slides highlight the unique breakthrough that set our innovation apart, not just in terms of performance, but also in sustainability and process efficiency. Let's begin with how we have revolutionized process efficiency. We successfully eliminated the pre-gel oven baking step, which was one of the most intensive stages in the paint shop. This not only reduces energy consumption, but also simplifies the overall painting process. Importantly, we achieved this without compromising the corrosion protection. The integrity and durability of the vehicle remain intact even with the streamlined process. This makes a significant step towards sustainable manufacturing, enabling a more agile and energy efficient production environment. Now let's look at the material innovation that made this possible. We developed a wet-on-wet sealant formulation featuring a novel polymer backbone and adhesion promoter. This allows paint to be applied directly over wet sealant, eliminating the drying and reducing cycle time. We also introduced a high-throw E-coat using branched epoxy structure. This enhances internal surface coverage and corrosion resistance, especially in complex vehicle geometries. Together, these innovations not only improve performance and durability, but also significantly reduced energy usage and operational cost, making our manufacturing process more sustainable, efficient, and truly future ready. Now, this slide highlights the dual impact of our innovation. That is, on one hand, it has environmental sustainability impact. On another hand, it has financial efficiency. Let's start with the environment benefit. By implementing sustainable material and optimizing our paint shop process, we have successfully 969 tons of CO2 emissions annually. To put that into perspective, it is equivalent to planting over 15,000 trees every year. These results clearly demonstrate that sustainability is not just good for the planet, it's also good for business. By reducing waste, utilizing energy efficiently, and reducing emission, we are creating a more responsible and resilient manufacturing ecosystem. With these benefits, Tata Motors commercial vehicle is setting a benchmark for sustainable industrial innovation. Thank you for listening. I appreciate your efforts. Thanks a lot.
Yeah, thank you very much. Looking at my fellow jury members for questions. Samaya, go ahead.
Thanks for your presentation. So your report is showing substantial CO2 reduction because you eliminated the pre-gel oven step from the process. However, this new formulation could also cause additional energy consumption and CO2 in the production phase. I'm just asking this, did you account for all the scopes of emission 1 and 2 and 3 to say, okay, this new formulation and process is reducing the overall energy consumption and CO2 emission, or just limited to that?
Yeah, thanks for the question. I think that's very relevant. So in our development, we have considered the direct emission of scope 1 and 2. So during the development, like the earlier sealant also will consume certain energy when you will make it. The same amount of energy in CO2 emission will happen in this new sealant also. However, we have not counted that because we will get it from our tier 1 and tier 2 suppliers. That will be scope 3. But that we have not counted. What we have counted is by removing the oven. Since that oven is running on by burning the fuel, we will be saving the CO2. So that is the counted in this.
Okay, so you have not measured the emission level of the production of this new formulation or material, and it could be more, it could be less, but you don't have any information about that.
So we have an estimate that it will be same, but we don't have exact data. We have considered from plant implementation.
Okay, so the overall energy consumption and emission still is not clear if that level of improvement that you mentioned addresses all the scope 3 emissions, right?
Yeah, so scope 1, 2 is, yes, right. Scope 3 complete is not considered. 1 and 2 is considered.
Okay, thank you.
Jose Carlos.
Thank you, Willie. Well, congratulations on your project. I appreciate how in the methodology you emphasize the use of TQM and how the organizational culture and the quality culture adds to this project focus on reducing the energy consumption. Can you please elaborate a little bit more how quality and in general culture finally adds to the success and the results of this project?
Yeah, thank you. I have mentioned that because this project could not be done only by one department of an organization. I am representing the engineering. However, on this project, various other departments like supply chain, the manufacturing, the quality, they all are involved. And having this mindset, we used to have this TQM training in our organization, and there are certain goalposts set for doing any project.
that how we should ensure quality. For example, while we will do test at lab level, what are all parameters that we should check? When you do trial in the vehicle level, what are all parameters we should check? So there has been a total quality management steps which has been followed across the development, and across CFT has done their part. So that is why I've told that we've used the TQM as a culture.
Thank you.
Okay, thank you very much. Ravikant, you still have a question?
No, I think they overshot the presentation, so I have several questions, but I will in lieu of time I'll let them go. Thank you.
Okay.
I am
Thank
sorry
you very
for
much.
overshooting the time. It has overshooted. I'm really sorry. It had overshooted by 2.5 minutes, I guess. I'm sorry for that.
No, you overshot by 10 minutes, not 2.5 minutes. It was 10 minutes, you took 20 minutes. But anyways,
okay.
That's Willy's comment, not mine.
Thank you all. And this concludes the presentations and Q&A of the second session. Indeed, we'll have a shorter break now of about 7 minutes until 13:40, when we pick up with the last session, where we have 3 more projects to see and to discuss. Thank you all. See you in about 6 to 7 minutes.